My name is Thorsten Schaub and I would like to tell you about the ASP solving process. To begin with, let's get an overview over this process. Our goal actually is to compute one or several solutions of a given problem. As in all approaches to declarative problem solving, we do so by expressing the problem in a formal way. In ASP, this is done by modeling the problem in form of a logic program. Importantly, this logic program does not only consist of rules, but also of first-order variables. In a first step, these first-order variables are eliminated by a grounder. It does this by systematically replacing all variables by ground terms in the language. As a result, it produces a propositional program that is free of all first-order variables and only consists of propositional atoms. Now, the resulting program is then taken by a solver that computes all classical or stable models of the original program. So we start by modeling the problem as a logic program. We then eliminate all first-order variables by a grounder. We solve the propositional program by computing all stable models of the original program. What is particular about this ASP solving process is that it is very elaboration tolerant. In the sense of John McCarthy, a small change in the world is reflected by a small change to the specification. And this loop actually is very tight, in the sense that you can nicely modify your logic program over time. But this is something you will experience in what follows. To illustrate the ASP solving process, let us look at graph coloring. Graph coloring is actually a pretty popular combinatorial problem, and in case you're not familiar with it, you can just read it up on Wikipedia. More specifically, the material I will be presenting below is taken from our book, where you can of course find complementary information about the whole thing. Now let's come to the actual problem of graph coloring. Of course, a graph consists of nodes and edges, and the goal of graph coloring is to assign to each node exactly one color, so that no two nodes that are connected by an edge get assigned the same color. This is of course an abstract problem. A more concrete one and popular one is map coloring, where the idea is, given a map with countries on it, assign to each country a color so that no neighboring countries get assigned the same color. Now let us see how we can solve the graph coloring problem in answer set programming. First of all, we have to distinguish between the problem instance and the problem class. In our case, the problem instance consists of the graph, which is itself composed of nodes and edges, along with some colors that we have to assign to the nodes. All three of them are represented as sets of facts, and for this we use the predicate symbols node, edge, and col. One way to look at this actually is that each concept is represented by a table, like in a spreadsheet or a database, but here expressed in a logical format as sets of atoms. To illustrate this, let's look at a specific graph. Now this graph consists of 6 nodes, 1 to 6, where each node is represented by an integer, and actually in this case we have a directed graph, and these 3 facts actually represent all outgoing edges going out of node 1. So we can go from 1 to 2, from 1 to 3, and from 1 to 4. Now that we have seen how to represent the problem instance, let's come to the problem class. Actually, the graph coloring problem can be nicely expressed via 2 constraints. The first one says each node must have a unique color, and the second one says that 2 connected nodes must not have the same color. These 2 constraints can be encoded in ASP in a straightforward way. To see this, let's just look at the corresponding encoding. Actually, I use LP4 to indicate code that goes with Gringo 4, but you may just choose the extension of your choice. Now, that's the encoding I'm using, and as you see, the first thing that is in this encoding are the different colors. There's red, green, and blue, and of course you may argue that this may belong to the problem instance. I rather have it here as more or less the 3 coloring problem, up to you. Now the heart of the encoding are of course these 2 rules here. And these are rules actually because there's a rule connective, which is this guy here, which can be read as an if. So this is the head, and this holds if the body is true. What you see here, this is actually a rule with an empty head. It has only a body and no head, and this is an integrity constraint. Anyway, let's look at this in more detail. First of all, it's important to see that this constraint here expresses this statement. That is, each node has a unique color. And the second statement, that two connected nodes must not have the same color, is expressed by this integrity constraint. Now let's briefly explain the syntax a little bit. And I guess a nice way to do this is to examine what the grounder actually does to these rules. Okay, let's look at the first rule first. Now, here we actually have a cardinality statement, which say, okay, each node must be colored exactly with one color. So we have here, we fix the node, and here we say that it must be exactly one color. This set here is a choice and expresses that we can choose among coloring node X with either red, green, or blue. This actually becomes clearer when we instantiate this rule. Let's just play the grounder and instantiate this rule, say, for node 3. This means we replace all occurrences of X here with 3. This is the first occurrence. This is the second one. And now we have to instantiate this set. And as in set theory, we check how we can make this condition here true. And we can make it true by replacing C by red, green, or blue. Let's just do this because it gives us a clearer idea how this will look afterwards. So we take this atom here and we instantiate it for red, green, and blue. That we get 3 copies. So the first one expresses that we could color 3 with red. The second says we could color 3 with green. And the third one says that we could color 3 with, guess what? Blue. Okay, now these are all the possibilities that we have, and these are the choices that we have, the options. And this cardinality, let's say adornment, says that exactly one of them can become true. Other things are possible, and you will see this in other videos or when you just practice a little bit more. Another little detail I should remark is that the grounder actually will simplify this rule because it knows that this is actually a fact and this is true, and hence it replaces it by true. This means it just deletes it here, and so this rule, the body will become empty and this rule will become a fact. And the fact will simply state a cardinality constraint. Exactly one of the elements of the set is allowed to become true. Okay, this is a sketchy introduction to choice rules and how the instantiation of them works. The instantiation of the integrity constraint is just analogous. You just pick an edge that is 2 nodes that are connected by this edge predicate, and you do this then for each color. There's for each edge you get 3 integrity constraints, 1 for red, 1 for green, and 1 for blue. Finally, I should mention what this line here means. This is actually an instruction to the solver and does not belong to the logic program as such, and it tells the solver to only output atoms with the binary color predicate and suppress all other outputs from the model. This encoding is not only neat and compact, but it also nicely reflects the ASP solving methodology. That is the way one writes nice and good ASP programs. So we actually have 2 parts here in this very compact encoding reflected by a single line. So the first one gives us a generator that generates potential solution candidates, and the second part is a tester that filters out valid solutions. Let me just summarize this on a little slide. So, as mentioned, the ASP modeling methodology rests on a generate and test approach, which can be seen as being inspired by complexity theoretic considerations. So you have an oracle that provides you with a solution candidate, and then you have a tester that tests whether these solution candidates provide valid solutions to your original problem. The generator is then normally implemented by non-deterministic constructs like cardinality constraints, because you want to have a multitude of candidates, and the tester then filters among them and is thus usually implemented by appeal to integrity constraints. In a nutshell, a logic program is then composed of several parts. For one, the problem instance, which is the data, a generator and tester part, and optionally an objective function to optimize your solutions or to find optimal solutions. Okay, now let's come to the fun part and run some of the systems.